welcome to actually Kanhere's PhD thesis defense. So I'm, actually it's a PhD advisor, and so I'll first introduce, Ashwin. How to forward next slide?
Maybe not.
Let's go. Cool. Okay, yeah. So Ashwin was a very cute baby. And then, yeah. And then apparently he had strong interest in science and especially physics from a very young age. And then his friends describe him as sometimes too scientific, and then such that they think Ashwin deals with his even personal issues from using a scientific approach. And then because of Ashwin's love of science and then physics, unlike most of his family members, who are almost all of them are medical doctors, and Ashwin took the path as an engineer. And then Ashwin is also a dog lover. And apparently when Ashwin was in middle school, and then his family were planning a vacation to US from India. For most of the kids, they will be really excited to go on this overseas trip to the US. However, Ashwin, he told the parents that he would rather stay and take care of their newly adopted puppy. And then apparently Ashwin is also was a competitive swimmer. And then, so when first got this photo, I thought it must be about some academic awards from his undergrad IIT Bombay. But then when I look closely, I realized, oh, he was the winner of 9 gold medals, 3 silver, 2 bronze medals for the IIT, Indian Institute of Technology swimming team. And then he was also a record holder for the state and then the university as well. And then apparently he was a national level competitive swimmer. And then during his time at Stanford, he continued his passion for swimming. Apparently, he and my 2 other students in our group, they swam from Alcatraz Island back to San Francisco. And then because actually I got a lot of inspiration from Ashwin, and because of them, I started to take beginner swimming classes. As of just a couple of weeks ago, I was finally able to swim for 100 meters nonstop, and that was a big breakthrough. So you keep inspiring me for that. And then Ashwin is also not just a nice lab member, but also friend with a lot of people in our group. And then, as you can see, he's always brings his unique humor and fun to the group culture. And what's more, because Ashwin is the tallest person in our group and also has the longest arm, so he has been our designated selfie taker. So whenever we need to take a group photo. So, and then Ashwin is also very optimistic. Speaking of that, so Ashwin, we look forward to your PhD defense presentation today. I wish you all the best.
Can you hear me? Awesome. Okay, so I'm not going to introduce myself anymore. Professor Gao did a great job of it. I also don't have any pictures of myself yet. But instead, I'm going to talk to you about the work I'm going to talk about in the presentation today, which is resilient GPS positioning using deep neural networks and sensor fusion with factor graph optimization. You might not know this, but you have a lot of positioning needs throughout your daily life. You might be a boat out at sea, at which point you need to report your position to the relevant authorities as well as boats around you using something called the automated identification system. This is so that they can monitor you as you load and unload at different ports, and also so that they don't collide with you. This is a great place because it's all open sky conditions. Everything is very nice. You're out in the open, not going to hurt a lot of people here. But you also have positioning requirements in tightly clustered, dense environments, which can be urban environments. If you're an autonomous vehicle, in this case, for example, you actually need very precise positioning because you cannot drift outside of your lane. And so that leaves you with like a half-meter bound on your positioning requirements. Both of these applications are knowing where you are, so you know where you have to go. There are also applications of knowing where you are, so you don't go where you're not supposed to go. The FAA has no drone zones, so you cannot fly drones without prior permission around airports and in a 15-mile radius in Washington, DC. And so they usually use your position to help you avoid these geofences so you don't accidentally go into those areas. If you were to end up going in an area where you weren't supposed to go and you're in trouble, someone needs to come get you to help you, which is where search and rescue comes into play. So people need to be able to locate where you are and then navigate successfully to your position so that they can save you. GNSS, Global Navigation Satellite System, of which GPS, the Global Positioning System, is the American counterpart, is a great system that can be used for these positioning applications because it can provide you positioning around the globe at any time of the day. However, the civilian GPS signal that people tend to use for these applications has some vulnerabilities. You have jamming, where someone can just prevent you from getting a fix. You have spoofing, where someone gives you an incorrect fix, and then just faults in the measurements which degrade your accuracy. All of those are going to affect these applications. Namely, for the maritime case, if you're someone who wants to evade sanctions, like there's some sanctions over Russia, over Iran, you can evade those by broadcasting spoofed positions to the AIS system and pretending that you're somewhere that you can be and not where you're actually in. In urban environments, if you're looking at autonomous vehicles or urban air mobility applications, the interference and multipath effects are going to cause degraded accuracy. Similar to the maritime case, you can spoof your position again here and violate the geofences, thereby causing problems and headaches for the FAA and federal authorities near DC. And finally, any incorrect navigation in a search and rescue application can cause the loss of a few seconds, which can have life-threatening consequences. In today's presentation, I'm primarily going to be focusing on spoofing and measurement degradation. And so one of the goals of any resilient GPS navigation system is to have some kind of fault mitigation because you want to prevent these errors from occurring or prevent them from affecting your position solution. You want to have some form of spoofing mitigation so that you mitigate the effects of spoof measurements. And then finally, because no one is going to tell you that they're spoofing you beforehand, and you're not going to know that faults exist when they do, you need to be able to mitigate either of those, depending on whichever one happens. Before I talk about mitigation, let me give you a brief recap on how GNSS positioning works. So you have satellites that are broadcasting signals. Through those signals, you can extract the satellite's position, velocity, and timing. And through those signals, you also measure the distance to the satellite. Now you start with some guess of where you might be, what your velocity might be, and what time you might be maintaining. You calculate the expected range for the position you have, and then find the difference between the expected range and the actual range that you receive. These are called residuals, and in this nominal case, they have some noise, which is zero mean Gaussian noise. You then use the residuals and your initial estimate and get a position update. Now, many times one position update isn't enough, and so you might have to do this iteratively, and so you keep updating your position until you've reached some convergence criteria according to your optimization, and you say, okay, this is my estimated position, velocity, and timing. Now, if you have faults, what they primarily do is introduce additive biases and degrade estimation accuracy. And a lot of these faults tend to be environment or context dependent. They also vary from measurement to measurement, and as a result, can be hard to model analytically. And they end up causing non-Gaussian residuals. Some examples of these faults can be non-line of sight signal reception, or NLOS, where you receive a reflected copy of the signal and the actual line of sight signal is blocked. Because the signal is reflected, you have more ranging than the actual signal did, and so the residual is going to have an additive bias. You can also have a case of multipath, where you receive both the reflected and the original line of sight signal, and if you lock on to the reflected signal, it's going to have an additive bias as well. These are primarily caused by buildings and glass facades of buildings in the environment. But you can also have cases where things don't happen the way they were modeled. There might be a satellite clock instability, which might cause a bias to enter there. Maybe the ionosphere isn't behaving the way you had modeled it to behave. And so you have incorrectly estimated the delay. All of these are introducing additive biases and violating the zero mean Gaussian noise assumption for a nominal measurement. Now, if you have spoofing, on the other hand, that's going to induce false positioning. For most civilian GNSS signals, the signal structure itself is publicly known and the signals are unencrypted. As a result of which, you can have a spoofer that broadcasts a copy of a version of these signals at a higher power. You start tracking these signals, and then the spoofer induces a false ranging measurement that corresponds to the position that the spoofer wants you to estimate. And so the position that you would have originally estimated, which would have been authentic, is no longer the position you're estimating because you've locked onto the spoof signals, you're using the spoof measurements, and you're inducing the position the spoofer wants you to estimate. This can cause deviations in your position, faults can degrade accuracy, and so it's important to be resilient to both of these effects, which is why today I'm going to be talking about fault mitigation, spoofing mitigation, and joint mitigation. Now, throughout my time at the Nav Lab, I've been looking at these problems from certain different aspects. For fault mitigation, I'll be talking about my work on improving GNSS positioning using neural network corrections today, but I've also looked at a combination of LiDAR with GPS sensors. For spoofing mitigation, I've been parts of teams that have looked at this from a Kalman filter perspective, combining odometry sensors, but I'll be talking to you about our work with factor graphs today. And then for joint GPS and GPS spoofing and fault mitigation, I'm going to talk to you about our framework using expectation maximization. I also wanted to give a shout out to one of our projects here, which is GNSS LibPy, which is an open source Python GNSS estimation library that I've been working on with Derek Knowles to simulate a lot of the measurements that we use for experimental validation here. And so the first contribution of this dissertation is going to be improving GNSS positioning using neural network-based corrections. The second contribution is factor graph-based spoofing mitigation using the Kanhere signal enhancement. And the third contribution is fault-robust GPS mitigation with expectation maximization. I'm just going to jump into the first contribution and talk about our work on improving GNSS positioning using neural network-based corrections. This work was co-authored with Shubh Gupta, who is the co-first author on this paper, who's unfortunately not here with us right now because he's in India getting engaged. Before I talk about our work, let me give you a brief primer on fault-robust GPS positioning. So you can also do detection and exclusion of faults, and you can do that at any point in the GPS processing pipeline. You can have specialized antenna-based methods. You can have specialized receiver processing techniques. And then if you don't want to use either of these, but just work with the measurements you received, you can also do consistency checking. Now, fault detection and exclusion typically results in a binary result. You have some measurements which you deem to be faulty, some measurements which you deem to not be faulty or fault-free. You use only the fault-free measurements for whatever positioning and navigation needs you have and discard the faulty ones. Mitigation, on the other hand, is deveighing some of the measurements that you consider to be faulty and using them less. You don't get rid of them. You might if the weights are close to zero, but you tend to use everything and deweigh certain measurements here. In this case, you can use signal characteristics like the signal to noise ratio or the elevation of the satellite, or you can even just use robust estimation to get rid of outliers. One of the things for any model-based parameter on doing this is they require expert knowledge and manual parameter tuning. A lot of times you have to figure out what is the parameter at which you consider something to be more faulty than the next, and so that requires expert knowledge. An alternative to these methods is to use data-driven methods. So instead of someone sitting down with some measurements and tuning the thresholds, you just show your method a lot of data and expect it to learn the parameters, thresholds, and models from this data. For some use cases like flagging multipath or NLOS measurements, there have been papers that have shown that the data-driven methods actually far outperform existing model-based methods. So one of the questions that we wanted to answer in this work was, what if instead of having some intermediate stage where you're considering a measurement to be faulty or multipath, we just learn end-to-end positioning? Would the model in that case learn models to mitigate faults as well? So doing this with deep neural networks was promising, but using deep neural networks for GNSS positioning can be challenging. GNSS inputs tend to be set valued inputs. So you can have 4 measurements, or 5 measurements, and you should still expect your positioning algorithm to work and be agnostic to the size of the actual input measurement set. Also, the order doesn't matter. So in this case, you can use 1, 2, 3, 4, 5 or 5, 4, 3, 2, 1. The output should still be the same, which is a challenge because common deep neural networks, like feed-forward neural networks, tend to assign specific parameters to specific inputs at specific locations. The other challenge was that the inputs of the GNSS positioning problem in general tend to be poorly conditioned. So your satellite variables, satellite positions can go from minus 20,200 kilometers roughly to 20,200 kilometers in all 3 XYZ directions. Your position can be minus 6,000 kilometers to 6,000 kilometers. And your pseudo range is also going to be 20,000 some kilometers. The problem comes in because the values of residuals, which are actually impacting your position after an initial estimate, are closer to 10 meters or 100 meters. And they tend to impact your position at the same scale as well. So you can't just divide anything because you would start losing precision because of this different scale of values. And you would have numerical instability for training a common DNN. So for our proposed approach, we proposed a neural network that solves both of these challenges. I'll give you more details on that shortly. But for this task, we start with a random initial guess in the vicinity of your true position. We do some data conditioning, then pass it to the neural network, and then the network is going to output a correction in the local frame of reference. The data conditioning is to stabilize the training process, and the neural network has a specialized component called a set transformer to handle set inputs. Let me talk to you about the data conditioning process first. So again, we're doing data conditioning to enable numerically stable training. And to condition this, we take all our inputs and put them in a local northeast down frame of reference based on the initial guess. So the initial guess is going to be the origin of the NED frame of reference. We convert the satellite positions to line of sight vectors. Line of sight vectors are typically unit normalized. And so now you have reduced all of that variation to variation between -1 to 1. And we convert the pseudo range measurements to residuals estimated for the initial position guess. We also output position corrections in the same NED frame of reference. So we have gone from a problem with 20,200 kilometers in the satellite coordinates and the pseudo ranges to something that has normalized LOS vectors and residuals that are of a smaller magnitude. And the same magnitude is for the correct position corrections. So the network is now relatively stable, more stable to train. An advantage of doing this is that the local input-output maps for the same residuals and LOS vectors apply worldwide. You could have the same satellite geometry and residuals here in Stanford as you have in Australia, and you're going to get the same kind of position correction, which helps because if you want to have more diversity in the estimates that you're making, it's good to have this kind of resilience to overfitting. To handle the set inputs, we used a set transformer in the neural network itself. Now, the set transformer has 3 components inside it. It has a transformer encoder, a transformer pooling layer, and a transformer decoder. The transformer pooling layer is what's of importance here because it combines all latent vectors for all satellites into a single vector. So if you have M received measurements, M can be anything here. It can be 4, 5, 7. It's going to convert all of these M by D features into one pooled 1 by D feature. Just because of how the set transformer is defined, the output isn't going to depend on the order of the inputs. And so as a result, just by using the set transformer, we have ensured number invariance and order invariance as well. A couple of notes on the set transformer that we used. The set transformer itself jointly learns the encoding, pooling, and decoding layers. So as a result, what it's going to learn is whatever function is best according to the data it has seen for estimating position corrections. Because we're training everything end-to-end. So we show it an example of what the correction should be, what the corresponding input is, and through showing it multiple cases of this data, just let the set transformer figure out what is the best kind of function that you can have in here. We validated this approach on simulated data as well as real data. For the interest of time, I'm going to talk about the real data validation here. We validated on the Android raw GNSS dataset that was collected for the Google Smartphone Decimeter Challenge back in 2020. It was collected in 2020, made available in 2021. The dataset itself had two sets of traces. training traces and test traces. We used only the training traces because in the training traces, they gave us access to the ground truth positioning. We needed the ground truth positioning for training our network and also for validating and testing the network. These training traces were split into 70% for training the network, 10% for validation to make sure that we weren't actually overfitting on any of the traces inside the training data set. And then we used 2 traces for evaluation. In particular, one of these traces, the one shown over here, was in downtown San Jose, and it was geographically not close to anything that the network had seen so far, because the network had seen a lot of highway driving on 280 and 101 before this, but it hadn't seen anything in San Jose. And also, it hadn't seen anything with the kind of environment that the this test trace had. One of the hyperparameters that we were also looking at was the initial randomness. So how off were you randomly from the true position in the initial guess? So just highlighting one particular trace here, the urban trace from San Jose. This was in downtown San Jose, which is not San Francisco or the island of Manhattan. So it's not absolutely terrible to work with, but it still has tall buildings and blockages because of overpasses and underpasses. So you still have some level of physical degradation of GPS signals. We compared our approach with 20 meters of random initialization error to an equivalent baseline that was weighted least squares that used elevation-based weights. Looking at the RMSE in the northeast direction, we see that our proposed approach outperformed WLS, and it also did so in all 3 dimensions together. So in this particular case, in the urban trace, our proposed approach was outperforming WLS, and so we used this to draw an inference that there was some effective mitigation of physical degradation of GPS signals that was happening here. However, this wasn't happening at the cost of all of the other data that we saw, those highway data sets. We also just compared the performance of a network on the entire test set to WLS. We chose for this particular case 2 instances of the network. So we compared a network with 15 meters of initialization error and a network of 30 meters of initialization error to WLS. So a couple of things that we observed here was that depending on the initialization in the north and east dimension, you either had performance close to WLS or performance slightly worse than WLS. But for both the networks, you actually outperformed WLS here. Another thing that we noticed was that the network does better in the overall error metrics when it's shown less initial random noise in the guess. So the 15-meter network outperforms the 30-meter network on both the north and east directions, as well as the down directions. And an unintentional consequence of showing it only the kind of training data that it was going to see at test as well was that the network somehow learned that the maximum magnitude of corrections it had to give for the 15-meter case was never going to be larger than 30, and for the 30-meter case was never going to be larger than 60. And so it would just cap off the corrections there, which is something that tends to happen when you're training neural networks. They tend to pick up on intricacies of the data that you really didn't want them to pick up on. However, this didn't really affect any of the results in the domain that we were looking at over here. So to summarize this first part, we proposed a neural network that estimates corrections to random initial position guesses. We used data conditioning for numerically stable training, and we used a set transformer to give set invariance to the neural network. We also validated our approach on real-world data, where we showed that it outperformed WLS in the vertical direction and in the north and east direction, depending on the randomness in the initial guess. So that was for fault mitigation using neural networks. Now I'll talk about spoofing mitigation using a factor graph and the chimera signal enhancement. I'll give you more details on which shortly. In this section, I'm briefly going to touch upon related work again. Then I'm going to talk about how we model GPS spoofing for FGO positioning and how we use the factor graph to integrate chimera in this process as well. And finally, I'll talk about some simulated experimental validation. So a quick refresher, although it's been 20 minutes, I hope you haven't forgotten this. GPS spoofing induces false positioning. So you have the spoofer broadcasting a signal at a powerful source. You track the spoof measurements and just induce a false positioning. One of the things is that the spoofer need not do this for just one-time instance. It's going to be doing this over time. So as you travel through your specific trajectory, the spoofer will continue to introduce small deviations and finally get you to whatever position it wants you to go to. As a result, there's a couple of notes that we can say here. The first is that all measurements at a particular time instance are going to be either affected by spoofing or unaffected by spoofing. Because for the spoofing attack to be effective, it has to consistently deviate your position, which means it has to consistently deviate all measurements. However, this likelihood is not the same across all time. Again, there are different approaches for detecting spoofing attacks and mitigating GPS spoofing. You can have antenna-based approaches again. You can have signal processing and more statistical analysis on the receiver front and towards the end of this with the actual received signals, or you can just encrypt the broadcast signals. That's what the military tends to do. They broadcast the PY and M codes. So if you don't know what the signal is supposed to look like, you can't broadcast an exact replica of the signal. However, most use cases tend to use civilian signals where things aren't encrypted. But there's a solution for that, where instead of encrypting the entire signal, you can insert encrypted watermarks into the signal. Now, because these watermarks are encrypted, you can't predict what the watermark is going to be before it has been broadcast. And so you can't effectively copy that watermark. You eventually, through different mediums, so this is Chimera for GPS L1C, which is going to be broadcast as a test signal on the NTS3 test platform shortly. They still say November 2023. There's still 7 days, who knows? But Galileo also has a version of this called the OSNMA, Open Service Navigation Message Authentication, which they're already broadcasting. In this work, we're primarily going to focus on Chimera, which is why I have a handy schematic here giving all the pertinent information that we care about for Chimera, which is that if you get the decryption key to decrypt these markers through the signal itself, you can authenticate every 3 minutes. If you have access to a secure out-of-band connection, like a secure internet connection, you can do so every 1.5 or 6 seconds. Now, what this means for us is that essentially you have these markers that are encrypted and embedded in the signal. You're going to receive a key periodically and decrypt these markers. So you're chugging along, you have encrypted markers, but you don't have the key to decrypt them yet. You get the key, you decrypt them, and authentication has been received, in which case you authenticate all the measurements in the Chimera epoch so far. Once this has happened and you start receiving new signals, start chugging along again, not knowing if they're nominal or authentic or spoofed until you get the key again or don't get the key, at which point you can make a decision. One of the problems with Chimera, even though it's great, is the relatively low latency of authentication. So for the slow channel, it's 3 minutes, and for the fast channel, it's 6 seconds. And a lot can happen in 3 minutes or 6 seconds, depending on your application. Planes can land in 3 minutes, and you can go through an intersection when you weren't supposed to go through that intersection in 6 seconds. So it's important to have some measure of authentication between these Chimera authentications as well, which is where we turn to self-contained odometry sensors. Now, a lot of these sensors, as examples of which here are cameras, LiDARs, wheel encoders, and IMUs, tend to have different sensing modalities than the GPS signal. And so any faults, any degradations, or any spoofing attacks in the GPS signal itself are not going to affect the estimate that you're getting from these sensors, which is how they can provide authenticated measurements, and in many cases do so faster than the Chimera authentication rate. However, you can't just use these signals all the time because they tend to measure odometry. And so they're measuring the change in position over consecutive time periods. Any small error in the rotation or position in this time period is going to compound with the passage of time, and you will slowly but surely drift off from your true trajectory. How much you drift depends on what grade of sensor you're using, but you will still drift. This is not a new thing. People know about this and have in fact used this in combination with GPS measurements to minimize the drift. So every time you get a nominal GPS measurement, in this case, blue because it's nominal, you make a correction, correct your drift, and then keep estimating between those GPS measurements with your odometry sensors. If you have a good enough idea of your state through the odometry sensors, you can also just use this to figure out if you're being spoofed. So you maintain an estimate of your state or position through the odometry. You compare it to the GPS state you're getting, and if there's a large deviation between them, you can say that there's a high possibility that you're spoofed, the GPS measurement isn't authenticated, and you should probably not use it. This has already been used with Chimera to continuously authenticate positioning. So in one case, you can estimate the position in the Chimera epoch between authentications using just the odometry. So every time you get the authentication, you backpropagate the state estimate and use all the authenticated measurements. But when you don't have access to authenticated measurements, you just use odometry, relying on the fact that the odometry is not going to be affected by spoofing attack, and you are in some sense maintaining an authenticated state estimate. You can also combine GPS and odometry in the Chimera epoch if the GPS is determined to be authentic, which is what I did when I was working with Tara on a paper that used extended Kalman filters for this. There's two requirements for any method that's doing this though. You need a method to determine how much deviation you have between the estimated GPS position and the odometry state. So you can use them if you deem them to be authentic, and then discard them if you deem them to not be authentic. And then you need a method of doing centrifusion to combine the GPS and odometry measurements when you do deem them to be authentic. Now, remember how I told you that this is actually going to be a window problem because you're probably going to be spoofed across a window of time? That's when factor graphs come in. So factor graph optimization-based centrifusion has been shown to give state-of-the-art positioning accuracy, and it tends to work on a window of position, states, and measurements. So in a factor graph, you have graph nodes, which are circles here, which are connected to factors, which are functions of the measurements. Now, the goal is to optimize over this window and find an estimate for these graph nodes. So you start with, again, some initial estimate, you optimize the loss function, go through this process, reach some convergence criteria, and say, okay, this is going to be my state estimate for this particular window. Now, you can have a window that continuously expands, or you can just collect data and post-process it with the entire window. But you can also do what is called sliding window estimation, in which case the window size is the same. In this example, 4. And then every time you receive a new measurement, you basically move the window over and discard the old state and measurement. And by discard, I mean you're no longer optimizing over it. You're no longer forming any new estimates of it. You've estimated whatever you wanted to. You're not going to change that estimate anymore. However, for 2, 3, and 4 in this case, which you did have previously estimated values for, you can still estimate things and use these initial estimates to improve your estimation. Now, for mitigating spoofing attacks, our proposed approach was to deweigh the spoofed GPS measurements. But for this case, we were using a factor graph with odometry and GPS measurements. Odometry was IMU and VLAN encoder provided. And to deweigh the spoof measurements, we assigned a switching constraint, in this case, SI for time I, that denotes the likelihood of authenticity of all received GPS measurements at that time. This is a scalar for each individual time value because we assume that the spoofing attack is consistent. And if you're spoofed at time I, all GPS measurements are going to be affected. Now, as you'll notice, SI is also circled here. So it's actually something that you're optimizing for. So the loss function that you optimize over is now going to be a function of the position states of your interest and SI. And intuitively, we formulated this loss function so that SI deweighs GPS measurements that do not match odometry. So nominally, GPS and odometry agree. SI will tend to be larger and close to 1. In the spoofed case, if GPS and odometry disagree, SI will be close to 0. And because it's being scalarly multiplied with the GPS measurements, it's going to deweigh these GPS measurements out, and you will tend to rely on odometry only. Now, if you're using Chimera, at the end of the Chimera epoch, you're going to get authentication. You're going to get access to your key. And because you're using a factor graph here, you're also probably going to have some states that belong to the same Chimera epoch. In that case, we perform loop closure and hang on. And propagate the fact that you have authenticated things. So SI should be 1. Your GPS measurements are authenticated. You should use them as much as you can and constrain everything in the optimization. So these constrained states we are no longer optimizing for, whereas if this was outside of the Chimera epoch, we're still going to estimate some value for this particular case of SI. So this particular approach we validated in simulation. The baseline was a factor graph with naive loss formulation, and we used a ramp spoofing attack for the second half of the trajectory when spoofing was present. So comparing the mean errors of the proposed robust factor graph and the naive factor graph, because you're not using GPS measurements to the full extent that you can be using them, there is some accuracy loss over here. So the naive case in nominal measurements uses all GPS measurements, which is the right thing to do, and actually has a better accuracy than the robust case, which deways them by a tiny amount, and so isn't relying on them completely. But this loss of performance in the nominal case comes at a much more robust solution in the spoofed case. So over here, the dashed line is, the dotted red line is the naive factor graph error in the spoofed case. So you'll notice that this almost immediately starts tracking the spoofed attack and shoots up because it's tracking the spoof trajectory. Whereas the robust method will not track this trajectory and instead tend to rely on odometry more and mitigate the effect of this attack. What's happening under the hood is that in loop closure, authentication is propagating to the previous times, but also in the nominal case, SI is consistently high and including the GPS measurements during this nominal operation. Whereas in the spoofed case, where this is the value of SI for the spoofed robust factor graph under spoofed conditions, there's no chimera authentication in this experiment, and also SI deways GPS measurements after spoofing begins. So spoofing begins at roughly 6 seconds, and after a second or so, SI starts falling sharply and then almost falls to 0 by the end of 12 seconds. And so SI is devaying GPS measurements in the event of an attack, but not doing so in the nominal case. There is benefit to doing loop closure. So if you don't do loop closure, for example, you're giving all of these GPS measurements some high weight, but it is still not 1, whereas you could probably gain accuracy by using all the GPS measurements that you deem to be authentic. And so doing that does show some improvement in the accuracy numbers here. And so essentially using chimera authentication as part of the loop closure in the window when you have access to chimera results in a slight accuracy improvement here. To summarize this part, we designed a robust factor graph optimization-based approach that uses chimera-enhanced GPS signals to mitigate spoofing attacks with odometry sensors. We devayed the GPS measurements implicitly that do not match odometry using the switching constraint and incorporate chimera authentication as a loop closure. And finally, we validated this on simulated measurements. Now, moving on to the third project, I'm going to talk about fault-robust GPS spoofing mitigation with expectation maximization. So I'm going to give you another reminder on GPS spoofing and how it compares to faults. I'm going to talk about some of the challenges of joint mitigation. Then I'm going to talk about a proposed approach of joint mitigation with expectation maximization, and then talk about some experimental validation. So really quickly, spoofing is going to happen because the spoofer is broadcasting fake signals to induce false ranging. Measurement faults are typically going to happen because of environmental effects or incorrect modeling. As a result of the nature of spoofing, you're going to get all GPS measurements that are consistent with this false position that the spoofer wants to induce. But here, there's no false position that anyone is intentionally trying to induce. So the biases might not match any particular position. They might, but that's pure happenstance. And as a result, when modeling these, we can say that GPS measurements which are spoofed are all equally affected at time I, whereas GPS measurements which are faulty are individually affected based on whatever fault might be there. So if you had an algorithm that was doing just spoofing mitigation, jointly addressing either case of spoofing or faults can be challenging. This is a toy example where we are going to assume no noise, and we're going to assume that any deviations from 0 that happen are because of the presence of outliers or additive biases. So consider the nominal case. You have everything 0 because everything matches what it was supposed to be. And so in reality, if you were to detect and remove outliers or mitigate outliers, you wouldn't want to mitigate anything here. In the spoofed case, everything is going to have the same kind of outlier, and they're all going to be consistent with some position. In this case, if we assume the real line, it's going to be 1 on the real line. In the faulty measurements case, you would have some which are consistent with the true case, but some which just have additive biases. So if you're doing spoofing mitigation, you would typically have a test statistic like the sum of the squares of these residuals, which you would use for detection or mitigation. Now, in this case, in the first case, the sum of the squares of the residuals is going to be 0. Since we're assuming no noise and that only the presence of these vulnerabilities is going to cause outliers, we can also say that 0 is the threshold. If you're higher than 0, then something's wrong. So in the first case, you get 0, which is the threshold. In the second case, you get 4, which is higher than the threshold. In the third case, you also get 4, which is higher than the threshold. Now, again, if you assume the consistent modeling that spoofing affects all measurements at the same time, what you're going to do is not detect any outliers in the first case, which is correct, detect all outliers in the second case, which is also correct, but detect all outliers in the third case, which is incorrect. And so what's going to happen is that these faulty measurements can cause false spoofing alerts. Another thing that happens is if you don't deweigh these faults, you're going to track the faulty measurement and degrade your accuracy as is. Now, the same thing, but with an algorithm designed for fault robustness. Fault robustness is going to look at something like the deviation of this statistic from the mean. So does anything stand out of this vector? So in this case, in the first case, nothing's going to stand out. They're all zeros. In the second case, nothing's going to stand out. They're all ones. In the third case, this 2 is kind of going to stand out because it's not a 0. And so if you were to flag these, you would not detect any outliers in the first case, which is correct. Detect the first as an outlier in the third case, which is also correct, but maybe not detect any outliers in the second case, which is incorrect because you don't actually want to follow these spoof measurements. And so if you have something that's doing fault robustness, spoof measurements can cause false negative alerts. So the goal of this project was to kind of take both of these problems and design an algorithm that could do either, depending on whether the measurements had faults or spoofing. So in this case, we are also looking at estimating position over a window of time. We were using Chimera-enabled GPS receiver with pseudo-range measurements, and we were using only IMU to provide odometry between these different time steps. And our approach was to estimate both the likelihoods of these vulnerabilities and the position. And so in modeling this, you estimate the likelihood of authentic GPS with one scalar value per time instance. You estimate the likelihood of measurements being fault-free with one scalar value for every single measurement. So depending on however many measurements you received at a time instance, you can have different scalar values here. And in the end, what you're going to do is estimate the position, the likelihood of authenticity, and the likelihood of being fault-free in this estimation process. You run into a bit of a causality problem here, commonly known as the chicken and egg problem, because for spoofing mitigation, you want to deweigh the faulty GPS measurements. You don't want to use them for spoofing mitigation because they can affect the test statistic. For fault mitigation, if the measurements are spoofed, you probably don't want to use them as well. And then finally, for positioning that is robust to faults and spoofing attacks, you don't want to use GPS measurements with faults or spoofing. And so I need positioning for this, but I also need this for positioning. So how do I solve this problem? One of the approaches that we could use to solve this problem is expectation maximization. So the idea behind expectation maximization is that you're estimating each of these iteratively for each sliding window. And as in the same window, as you iterate through, you use estimates from the previous iteration for the next iteration. Now, how that would work is something like this. For initialization, we make some assumptions and use the Chimera signal enhancement to validate those assumptions. More on that in a bit. You initialize these estimates and then go into the first estimation window, where using the initial estimates that you've initialized with first, you estimate the likelihood of authenticity of GPS. You then use this estimate to estimate the likelihood of fault-free GPS. And then you use both of these that you've just estimated to estimate position. Now, you might have accidentally incorporated some faults because the initialization was for the previous window. So you go back and in the next iteration, estimate the likelihood of authenticated GPS using the likelihoods that and positions that you estimated in the previous iteration. You do this for faults again, you do this for positions again, and you keep doing this until you reach some convergence criteria that you might have defined. Once you converge, you get an estimate of position, the likelihood that the GPS measurements are authentic, and the likelihood that the GPS measurements are fault-free that you can then use for the next estimation window, where you do the same thing and get the same kind of estimate. For initialization, we do rely on the Chimera signal enhancement. So we initialize with the assumption that there are no faults and there is no spoofing. We can make the no spoofing assumption because we are initializing in the Chimera epoch once Chimera authentication has been received. So we know for a fact that things are not spoofed. And we make the assumption that there are no faults, working under the assumption that the number of fault-free measurements that you're getting through GPS and odometry is more than the number of faulty measurements that you're getting. Once you form this initial estimate, you then move the window, propagating this initial estimate for the next step of the EM estimation. In particular, in the EM estimation, when you're estimating the likelihood of authenticity, we'll be using sensor level redundancy. So we're looking at different sensors independently, not at measurement level redundancy. And then we deweigh the residuals with GPS fault-free likelihood from the last TM iteration. So if these are the true labels from our toy example, and let's say everything's going really well, in the previous iteration, you had actually estimated these likelihoods that the GPS measurements were fault-free. You take an element-wise product and then end up using these residuals for estimating authenticity. So as a result, this fault was estimated to be there, and its effect was removed when we were estimating the likelihood of spoofing. You then carry on, estimate the likelihood of fault-free GPS, estimate the position by deveighing the spoofed and faulty measurements, and keep doing so until you reach some convergence criteria, like I said. We also simulated this work. We validated this work with simulation. For the spoofed path, we considered a ramp attack. For faults, we considered a constant set of 2 faults. The baseline methods that we considered here were a naive factor graph with no mitigation, then a factor graph with only spoofing mitigation, and then a factor graph with only fault mitigation, and then finally also odometry only, just to make sure that we were gaining something by combining GPS with odometry. The GPS pseudo ranges and positions that were simulated for this were realistic and were generated using GNSS LibPy, our lab's in-house software simulation tool that I've been working on with Derek for the last 2 years. And so right now I'm just going to talk about the mitigation of faulty measurements and then spoof measurements. So in this case, the EM estimate error is over here in green. The odometry estimate error is here. And this is a method for spoofing mitigation. The method for fault mitigation works as well as our proposed approach over here because it's specifically designed for this scenario. So you'll notice that our EM estimate is outperforming the odometry estimate, and the spoofing mitigation in this case just tracks the faulty GPS position. It's not able to mitigate anything in this case, despite the magnitude of the fault being quite large. So a look under the hood, our method is actually estimating the likelihood of authenticity as high here. It's not deveighing all of the measurements at any one instance. And in this fixed set of 10 measurements, the first 2 measurements are faulty, which it promptly deveighs because they don't match everything else, and then continues to give everything else a high weight. So that's how our proposed method is actually able to mitigate the presence of faulty measurements. Again, for spoof measurements, we have an odometry estimate. We have now a method designed purely for fault mitigation, which you can't actually see because it matches our proposed approach almost very well for the first half and then starts tracking the spoof trajectory very well. And we also have an odometry estimate here. Our proposed approach doesn't do as well as odometry in this case, but it still does mitigate some of this effect of the spoofing attack. And it's doing so by estimating the likelihood of authentic GPS here, which as you move across the windows, drops to 0 and then just stops using GPS measurements. An interesting note, and the reason why also fault mitigation is not able to successfully mitigate the spoofing attack is because there's 10 GPS measurements. Most of the measurements that the graph is seeing are saying that nothing's wrong, follow this trajectory. And so the graph actually gives them a high weight and just follows that trajectory. In our proposed approach, once you've completely deweighed those measurements, it's actually a local minima to assume that everything is fault-free because of the scalar product they're not going to be used anyway, which is how our approach is able to mitigate these spoofed attacks. So to summarize this part, we proposed a modular expectation maximization-based architecture for jointly mitigating spoofed and faulty measurements, depending on whichever exists for GPS-based state estimation. And we validated our approach in simulation, showing the mitigation of faulty measurements and GPS spoofing attacks. So overall, these were the 3 projects that I worked on over my PhD that I talked to you about today. This work is in no way, shape, or form completely done. So for GNSS positioning with neural networks, there is a lot that we can still do in combining model-based approaches with data-driven methods, because the GNSS estimation problem is so geometrically well-defined. And if you're doing this over a window, there's also dynamics that you can consider. And people have spent a lot of time and effort modeling these. So it would be great to combine them with data-driven methods. And actually, I worked on a paper with Shub last year where we did some of this initially, and some other work from our group has also done this, but there is more potential to be explored here because this problem has not been solved. For spoofing mitigation with the factor graph optimization, just modeling the spoofing attacks is okay, but it's not enough because there's a lot of requirements on how good your method should do. It should use GPS and not give out false alerts. And so modeling that into the factor graph is also an important part. Finally, for the joint mitigation of GPS spoofing and faults, my hypothesis is that this method should be modular and you can swap out any method for estimate deveying spoof measurements, deveying faulty measurements, and state estimation, but that's just a hypothesis. And so that hypothesis needs to be verified to make sure that this is indeed a broad architecture that you can use for different methods. So just to summarize, in the first paper that I talked about today, I talked about improving GNSS positioning using neural network-based corrections. We did some data conditioning and used a set transformer to have set invariant results. In the second part of today's presentation, I talked about factor graph-based spoofing mitigation using the Kanhere signal enhancement, where we modeled the spoofing attack and formulated a specific graph and cost function for that, and then used Kanhere as loop closure. And in the third project that I talked about, we did joint spoofing and fault mitigation, used the Kanhere signal for initialization, and then estimated the likelihood of spoofing attacks and faulty GPS measurements for resilient positioning. None of this work would have been possible without my sponsors, the Air Force Research Lab, who very graciously funded and supported me during my PhD. It would also not have been possible without my committee members and my advisor, Professor Grace Gao in particular, who mentored me and taught me how to do research from my master's and PhD because I had not done research before that. Professors D'Amico and Walter, who gave me very insightful comments during my Greenlight meeting, which I hopefully incorporated some in the third presentation and am planning to incorporate in the thing I talked to you about as well. Dr. Sherman Lowe, who also has been part of the ION organizing committee, and all of the conferences that I've gone to have been ION conferences. Thank you for that. And then finally, Professor Kapitanovich, who said yes to chair my defense on the day before Thanksgiving without having ever met me. To all of my committee members who are here today, thank you very much. And to everyone who's on Zoom, this is who I was talking about. I would also like to acknowledge my lab members who are all here. They're not just coworkers and colleagues, they're also great friends, because of which they were here an hour early. I've had a lot of fun hanging out with you at conferences, in suits and boots, outside of suits and boots, and just parties in general, lunch discussions, coffee walks, and even attending a couple of odd weddings here and there. I also want to thank my friends. We'll take some time because this, I would also like to thank my friends who have goofed off a lot with me over the years, had exciting ninja vacuum cleaner battles, which was all fun. The PhD would not have been half as enjoyable as it was without any of you guys. And I can very happily say this because one of my friends who's not my lab member, two actually, are here today, four actually. I would also like to thank my family members, my parents, my brother, my grandparents, and Tango and Bruno. It is also my sincere belief that this is the cutest picture you will see in this entire presentation. That's Tango when he was like a few months old and my father holding him. And finally, I would also like to thank Ashwin, who was not supposed to be here today because she's in Norway on an exchange program, but then surprised me yesterday. If any of you want to see what a dumbfounded Ashwin looks like, she has the video. Thank you for being an excellent support throughout this process. Thank you for laughing with me and making me laugh when I wasn't necessarily in the mood to laugh. And finally, thank you to all of you who are here the day before Thanksgiving, when it's technically a vacation, and attended this presentation. I hope that I am able to answer any questions that you might have after this.